points. It doesn't have to be like across a battery or whatever. It can be anywhere, all right? Voltage is also the force that moves charges. It's like basically the energy available per charge, okay? So a positive test charge will experience a force in the direction of the electric field due to the voltage applied to it from the potential field, right? So a negative charge will move in the opposite direction. So let's say I have like my potential field. There's just a whole bunch of numbers everywhere, right? And then I've got a point charge over here. It moves in the direction that decreases the potential the fastest, okay? Yeah. The work done to move the charges comes from the electric field. So you have an electric potential energy due to the electric potential field, all right? And the charge wants to move from an area of high potential to low potential. So when the charge moves, it's converting its electric potential energy to kinetic energy, all right? Any questions about this? Great. So it's important to note that voltage is only defined between 2 points, and potential is with reference to a ground or to a zero. Just like how height is reference to whatever you say is zero, potential is also reference to whatever you say is zero. Okay, so sometimes we will say that zero is ground, sometimes we'll say that zero is like infinitely far away, whatever. You just choose a zero, and then what is the potential relative to that zero all around you? Okay, so this is how voltage works. So whenever we have circuits, we define a ground, which is a point at which this is 0 volts. And then we just say, okay, like what is this battery and that power source and whatever voltage source, you know, how do these affect the voltages in the circuit around that with reference to this 0 volt? Okay. All right, so now current. So a voltage between point A and point B will cause all the charges to move from point A to point B. They will experience a force, all right? The implication being that point A has a higher potential than point B, okay? So charges will flow from point A to point B. The amount of charge per second moving through any point in space is the current through that point, okay? And again, remember, voltage can be between any points and current can be at any point also. All right, it's just how much charge is flowing through that point in space at any given time. That is current. Okay, it doesn't have to be through a conductor or anything. It's just through a point in space. All right. And I know that sounds like I'm being like confusing for no reason, but I swear to God, like it matters. Current does not have to be through a conductor. And when you are designing real circuits, this matters. All right. So conventional current is the motion of positive charges, like test charges that we talked about earlier, which is just any charge with a positive plus 1 coulomb of charge, right? So this is how most physics is defined. But real current is motion of electrons through a circuit. Unless for some reason you have like positive ion carrier, don't do that. So generally when you have like copper conductor, you will have your current will be motion of electrons, which is negative. Therefore, real current is in the opposite direction as conventional current. Okay, so whenever we do physics, or whenever we do like basic electronics calculations, like V equals IR or whatever, which we'll talk about later, we're always doing conventional current. Okay, but in reality, the electrons are flowing in the opposite direction of what you say the current flow is. All right. This is absolutely fine and it does not affect the physics or the math at all. Okay, it affects very, very deep understanding of how the behavior is at a subatomic level when you're doing like field understandings. Okay, but we'll talk about that later in the course. For now, just understand that the electrons are actually moving opposite to what you say the current is going. All right, because current is talking about motion of positive charges. Okay, great. All right, I'm going to talk about resistance now, okay? So remember how we said that the water pipe is thin and therefore it's hard to push water through the pipe? Realistically, this is all we care about for most electronics, okay? So what I'm talking about now is what resistance really is, okay? So the reason why I want to talk about this is because I want to say that resistance doesn't only make current harder to flow, it also causes the current to heat up the wire. And this matters because if your wire melts, it's over, right? But in reality, you can just remember that and you don't have to care what I'm about to talk about, okay? I'm just telling you this because I think it's important, because I think it's interesting. All right. So resistance, again, doesn't have to be in a conductor, can be through anything, okay? So whenever you have a current moving through space, when they move through space, they will usually hit some kind of charged particle present in the conducting medium, which can be air, it can be water, it can be whatever, okay? So all of the charged particles in the medium have electric fields of their own. So as the electron moves, it gets deflected off of the electric field of the charged particles. And this disrupts its velocity. So it decelerates the electron. So the electron is always experiencing a force from A to B because of the voltage across A and B. So it will accelerate, then decelerate, and then accelerate again as it continues to hit more and more charged particles. This is what resistance is, okay? We are slowing down the speed of the electrons because it's hitting stuff along the way, all right? So as it hits stuff in the medium, the particles of the medium gain energy in the form of thermal energy. They vibrate when the electron hits it. So therefore, we lose the kinetic energy of the electron to the thermal energy of the medium, and the medium heats up as you pass current through it. So depending on how much current you pass through, the medium might heat up a lot. And this can be problematic when you do real circuit design. Okay, so I'm just throwing it out there first. The current will heat up the wire when there is a resistance, and nobody actually cares why. Okay, great. Any questions? Good. Okay, so now we talk about Ohm's law. This is like what by far the most important thing you care about in electronics other than voltage move the charge. Okay, so V equals to IR, which means that voltage is the product of current and resistance. Okay, so basically all like 95% of the things that you interact with in circuitry will obey this somehow, okay? And whenever it doesn't obey Ohm's law, we call it a non-ohmic conductor, and then like we just cry about it, all right? But generally, Ohm's law applies to most things that we do. So for any given potential difference between point A and B, it can only push as much current from point A to B as the resistance between point A and B allows, okay? So if you have more resistance, you can push less current if you have the same voltage. Important. Nobody cares why this is the case, but everyone who wants to build circuits needs to accept how Ohm's law is used. And we'll have a lot of examples later and hands-on that shows how Ohm's law is used, okay? But I want to be clear that nobody cares why V equals to IR. Okay, with that in mind, let's talk about why V equals to IR. So, again, we don't care, but I think it's interesting, so I'm going to talk about it, all right? So when you have point A and point B, and you have a potential difference across it, all the electrons between A and B will experience a force from A to B. So they'll all move this way. Every single electron will accelerate. But because the medium has resistance, the electron is decelerated as it encounters charged particles in the medium. And then it accelerates again. This repeats really fast because there's a lot of charged particles in the medium. So therefore, you have a lower average velocity as you accelerate and decelerate. All right. So we call the average speed of the electrons their drift velocity. And this is way slower than the speed of light, by the way. The electrical signal travels at near to the speed of light, yes. But the actual electrons, they don't actually move that fast. Okay. Anyway, nobody cares. What we care about is that when you have a higher potential difference from A to B, you have a greater force on the electrons, which means they accelerate harder. Because they accelerate harder and they decelerate the same amount because I haven't changed the resistance, we have a greater average drift velocity. Since the electrons are moving faster, we have more current. Okay? If I increase the resistance, then the electrons are decelerated more often, which means that they have a lower average velocity, and hence we have lower current. That's it. Okay? Again, nobody cares. I think it's interesting, but just accept V equals to IR and all is good in the world. No problem. You can build great circuits without knowing why. Okay? Okay, so we're going to teach you how to apply Ohm's law to circuits. This matters because when I have current through a wire, I need to know if the wire can handle the current or if it's going to overheat. Okay, if a wire heats up, then its resistance will increase. And then this is a runaway effect if it heats up too much. Okay, we also need to know the voltage across our components in the circuit because components have a maximum voltage rating. Most components will simply explode if the voltage across them is too high because each component has a certain resistance and you put too much current through it and they heat up and blow up. Okay. Therefore, we also need to know what resistance we need to add to our circuits in order to guarantee safe voltages and currents for all of our components. And we'll show you some proper examples right after this. Any questions so far? Have I gone too fast? Yes. So Okay, imagine like, let's say I've just got like 100 people in a room and I just want to walk past them, but they're all standing still. It's not that hard, right? Then if they all start dancing in place, then it's like they're all vibrating all over the place and I'm going to hit some of them along the way for sure. The resistance increases as the thermal energy of the medium increases.
Are there objects that do the opposite?
Yes, but don't use them. Yeah. Like I think usually it's like heaters which will have this thing. So you have this thing called a positive or negative temperature coefficient, which says how the resistance of the heater changes as it heats up. So you can read more into that later, but basically like it's very useful in some cases and very scary in some cases.
So there's a sensor called a thermistor, and there's PTC and NTC. PTC is where the resistance increases, then NTC decreases.
Yeah. Yeah, so usually when we say that here is Ohm's law, right, we are assuming that the temperature of the system is steady and is not changing over time. This is an assumption that we use, because if we actually do like a second by second application of Ohm's law, then like we have a dynamic system now and it's annoying to simulate. Normally we don't care for designing circuits. Okay, yeah, okay. So I'm going to talk about series and parallel. I'm using the working assumption that you have been shown the shape of a series and parallel circuit. Okay, but I'm gonna show you in a second. I want to just explain. For components in parallel, you have different branches of the circuit in parallel, right? The voltage across each branch, like where the branches connect, is the same. But the current in each branch can be different. For components in series, there's only one long branch. The current is the same through the whole thing, but the voltage across each component can be different. If that sounds alien to you, we're going to go over the examples in like 2 seconds. Okay, so here is a series and parallel circuit. So series is on the left and parallel is on the right. Okay, so for a series circuit, can you see my cursor? Okay, good. So for a series circuit, let's say I've got a 10-volt battery here, which means I've got a 10-volt potential difference across this circuit. So 10 volts here and 0 volts here. This is why I arbitrarily assign. I could also say this is like 90 and 100 if I wanted to. It doesn't make a difference, okay? Because the difference is 10. And all we care about in circuitry is potential difference, not absolute potential. There's no such thing as absolute potential, all right? So I have an 8 ohm resistor here and a 2 ohm resistor here. So the 2R and the 8R, okay? R1 and R2 are just the names of the resistor. Don't care about it, all right? So for the resistance of components in series will just add up. So I have total resistance being 8 plus 2, which is 10 ohms, all right? So V equals to IR, right? 10 volts across 10 ohms, I have 1 amp of current. So there'll be 1 amp of current that flows through the entire circuit. So 1 amp that flows through here, 1 amp that flows through here, because they're in series. Current through the whole thing is always the same, all right? However, the voltage across each component can be different. So we have established that the potential difference across the entire circuit is 10 volts. But what about just the potential difference between here and here, right? So we know the current through this resistor is 1 amp. V equals IR, right? So I know my R, I know my I can tell that my V is 2 volts. 2 equals 1 times 2, brilliant. And then same here, I have 8 ohms and 1 amp. So therefore I have 8 volts through it because V equals to IR. Is this acceptable? This is fine, right? Great. So this is a basic series circuit, okay? And notice we care about the potential difference across each component and across the whole circuit, all right? But we never care about absolute potential because there's no such thing. I just assign something to be 0 volts and then that's it. I could also say that this is 0 volts and this is minus 10 volts. The system does not change at all, okay? All right, this is a parallel circuit. So with a parallel circuit, we have multiple things in parallel and they have branches of the circuit, right? So here's one branch and here's another branch, and then everything returns back to ground. Okay, so again, I say that here is 10 volts and here is 0 volts. This is outside of my branch system. And then within each branch, what is the voltage? So the voltage across each branch is always going to be the same. It's just 10 volts across this one and 10 volts across this one. All right. But the way that we calculate the resistance of the whole circuit is with reciprocals. Life is just like that. So if I use this equation, the reciprocal of the total resistance is reciprocal of R1 plus reciprocal of R2, which in this case I've labeled R3 and R4, sorry. Then I will find the total resistance of the whole thing to be some number, which I forgot. And then I get 6.25 amps as my result. Okay. So notice how, even though I've got the same resistors, they are in parallel instead of in series. And I've got way more current through the series version than the parallel version. Through the parallel version than the series version. Because when you put stuff in parallel, the resistance goes down, not up. Resistance goes up when you put them in series. Okay. You can think of it as like you have two thin pipes, which are the resistors, right? And you put them next to each other, the cross section of them add up, so more current can flow through. Versus if you put the thin pipes in front of each other in series, now you have to go through both resistances, so it's harder to push current through. This is the water analogy of series versus parallel. All right. If that helps, then good. So now I have my total current through the whole system. So when I enter the branch and when I leave the branch, this will also be 6.25 amps. But within each branch, the current within each branch can be different, even though the voltage across each branch is the same, because the resistance of each branch can be whatever, right? So I know I have 10 volts across this resistor. I have 10 volts, I have 2 ohms, so I have 5 amps through this. And similarly, I have 10 volts through here, but I have 8 ohms here, so I get 1.25 amps of current through this, because again, V equals IR, right? This is fine, right? Everyone's okay with this? Notice how the total current through the branches is equal to the current that went into the branches. Good. This is like conservation of charge or something. I forgot if that's a real thing. It should be a real thing. Yeah, okay. So everyone accepts series and parallel and what series and parallel means, right? Okay, great. Okay, side note, everyone learned batteries as a voltage source in primary school. But in real circuit design, voltage is just between 2 points. Okay, there is not necessarily a battery that is simply voltage and you just do whatever with it. Okay, so stop thinking about batteries. All right, voltage is just between 2 points and that's all. So we are generalizing the system now. Voltage can be between any 2 points. Current can be through any point regardless of conductor or not. Okay, and resistance can be inside a conductor, can be in an insulator, can be wherever, can be an empty space. All right, everything is just between points and it's just all about how the charges move, regardless of whether it's inside a copper wire or not. And this will prove to be important later. Okay? Yeah, so these are markers which you are going to see me use for the rest of the course. These are schematics from a circuit design software, which I will tell you more about next lesson or the lesson after that, I forgot. So this marker here is a power flag, and it says that there is 5 volts at this point. And this is ground, which says there is 0 volts at this point. Ground is always 0 volts. Okay. If it's not, then that's very bad. And we'll show you when it's not in like lesson 6 or 7. Okay. Anyway, tangent. We have voltage between points and that's it. There's no more battery. All circuits for the rest of the course are going to be using power flag and ground flags. Okay. So for this resistor in this circuit here, I show that I have 5 volts across it because I have 5 and 0 volts. So there's a potential difference of 5 volts. Okay. For this parallel circuit, again, I have a potential difference of 5 volts across the entire circuit, which means that the potential difference across each resistor is also 5 volts. Fair enough, right? Okay, great. Everyone comfortable with these symbols? Yes, good. Okay.
Okay, so for Kirchhoff voltage law, basically the loop, so it's an extension of Ohm's law, and as you can think of it as like you're walking around a hill, a mountain. As you go up and down the valleys, and you walk in a circle, you go back to the same point, and the height is you'll be back at the same height. So you can think of it in the same way as in circuits. So in any loop, and in any loop, what you get is the voltage between A, B. Once you add all the voltages together, you'll get 0. And is the same analogy as in when you walk around a circle around a hill. Yeah, so that's good. Yeah, this is voltage.
Oh, so this is wrong. This should say voltage.
Yes.
Okay, yeah. In case anyone was confused, this should say voltage. Yeah. Sorry, Joseph, continue.
Yeah. Sum of all voltages in the loop is 0. Okay, next is Kirchhoff current law. So Kirchhoff current law states that current coming into a node is equivalent to current going out of the node. So can think of it using the water analogy as the amount of water flowing into a point in the pipe is the same as the amount of water flowing out of the pipe. And that is as simple as it gets. Kirchhoff current law is that simple. And we'll go through some examples later on using these laws to calculate the voltages and current across each resistors and at each point in the circuit. So there comes a point where you encounter multiple voltage and current sources in a circuit. And so what do you do in this situation? So I'll teach you a technique later where you can, with a voltage source, you can replace. So all batteries are voltage sources, which means they provide a fixed voltage that you know. And there is also a current source. And so for voltage sources, you replace, you analyze one voltage source first. So for instance, in this circuit we are seeing here, we analyze battery 1 first. And so you replace battery 2 with a short circuit. And then you analyze, you calculate all the voltage just across each resistor and all the currents. And then you do the same for battery 2 while replacing the battery 1 with a short circuit. So once you get all the voltages across each resistor, you can add them up together. So that's what the superposition essentially says. You can add up the voltages together when you analyze each voltage sources independently.
Okay, we are going to do some proper circuit analysis now after applying V equals to IR. I am going to walk through most of these examples, except that one of them which you won't tell for you. And then we'll like see each other's work. Okay, the objective now is to get you comfortable with applying V equals to IR. It's bloody simple, do not worry. Okay, V equals to IR, and then of course also the way that you calculate the resistances in series and parallel circuits. Okay. All right, great. So this basic circuit, we have 5 volts across the whole thing. So here's 5 volts and here's ground, right? So we have this one resistor in series with this parallel system. So we treat the parallel system as one giant resistor of currently unknown resistors. So let's start by finding the total resistance of this parallel system. All right, and then we treat this as one resistor, and then we analyze the whole thing as a series. Easy. So we have 1 over the total resistance is 1 over 8 plus 1 over 4. Remember, we're adding up reciprocals for parallel circuits. So we get 3 over 8 as the reciprocal of total resistance. This is 3 over 8 ohms. Okay, so therefore my total resistance is 8 over 3 ohms for this parallel system. So I can replace this whole parallel system with a single resistor here and ignore this much. And this resistor is 8 over 3 ohms. Okay?
So you resolve parallel first, then you add it up.
That's right. We simplify the system by like kind of like compressing complicated areas into small parts. So we take this whole parallel system, we just treat the whole thing as one resistor. Then we can analyze the whole circuit, right? Okay, great. So we're doing things slowly and methodically, one little bit at a time. If you try to do the whole thing at once, you will cry. All right. So now we take this resistor and we add it to the resistance of this whole thing being one big resistor. So I have 4 plus 8 over 3. This is 20 over 3 ohms. So that means the total resistance across this entire area is 20 over 3 ohms. Okay. Now I apply V equals to IR to the whole thing. So I have 5 volts across a 20 over 3 ohm resistor. So what is my I? My I is 3/4. Is this acceptable? Great. So I have 0.75 amps through the whole thing. So 0.5 amps here at the entrance point of the circuit, which means that 0.75 amps through this one resistor, and it means that there's 0.75 amps through this entire parallel system, because this whole system is in series with this, right? Resistance across the current through this must be current through this whole system. Okay. Now, what is the voltage across this resistor? Because I need the voltage across this resistor because I need the voltage across this parallel branch. If I don't have this voltage, I cannot analyze the parallel system, right? So I have a 4 ohm resistor. 4 ohm resistor, 0.75 amps through it. V equals to IR. So now V is my unknown. What is the potential difference across? So I take 4 times 0.75, I get 3 volts is my potential difference across this resistor. Now, the total potential difference across this whole thing is 5, which means if this is 3, then the potential difference from here to here must be 2 volts. 2 volts across the entire parallel network, right? Fair enough? If anyone is confused, do not be afraid, okay? Just let me go too fast. So that means I have 2 volts across each branch in the parallel circuit, because in a parallel system, every branch has the same voltage across it, right? So I have 2 volts across this resistor and 2 volts across this resistor. No problem. 2 volts across this resistor and 8 ohms in this resistor means I have 0.25 amps through this. Again, V equals to IR. 2 equals 8 times 2, 0.25, right? Here again, 2 volts across my 4 ohm resistor. Therefore, I have 0.5 amps through this. Now we see the wondrous Kirchhoff current law. See, this is a node here, right? This node says that, look, I've got like splitting stuff, right? So I've got 0.75 amps entering, and I've got a total of 0.75 amps coming out. 0.25 plus 0.5 is 0.75, right? So current in equals current out. This is very intuitive. It didn't need to be a whole ass law, but they made it one. All right. Same here. 0.25 plus 0.5 amps is going to merge back into 0.75 amps down here later. All right. Okay. Any questions about this? All good, right? Who hasn't done it before? Just curious. Everyone's probably done it before, and like, I don't know, at some point. Okay, sure. Anyway, let's move on. So, oh, I thought I had more examples. Okay, now is the now is the one that everyone has to try. Okay, so all right. So this is okay. Remember, it's the same shit. All right. So now this whole thing is a parallel system first. So we have a parallel system with 2 resistors here, and I have another branch here. So this is one more branch because I split it into 2 first. Then this branch has 1 resistor in series with a smaller parallel branch. Okay. So don't worry, analyze bit by bit. I hope everyone has paper or something. I forgot to tell you to bring paper. Yeah. If not, you can use the whiteboard. I have a marker here. Okay.
Marcus, I have the curse of being unable to read and won't listen.
It is okay. You can read on my computer. I do on my whiteboard. Oh, oops. See closer. It's okay. I can spell bad.
Are you sure about this? Asking an engineer who is all that.
And you can see where we got.
I can show them. We're doing this in JC, right?
I mean, like, it really is nothing, right? Like
But it's there, not there.
Yeah, I get it.
Are you asking to resolve that? Are you asking what the law is?
The law is actually like I in equals I out. It's no problem. Yeah.
This is for every component.
No, for every time the circuit, the wire branches. So every
It's not
time,
every point.
yeah, every
All
time,
of components.
correct. It's not all components. It's about every time the wire branches. Because that's what we call a node. Yeah.
But no, there's 4 times 7. I didn't want to calculate that. I didn't know. What is Balls. Parallel does not add up. The resistance. The reciprocal adds up. But the penalty adds up. So, no, so this is, so if you have like, for example, 8 resistance and 5 resistance, your total should be something like 4 resistance. If it's not, then you're doing something
So
wrong.
you add up the reciprocal of each individual branch. So let's say one branch is 8, one branch is 5, right? So I get 1 over 8 plus 1 over 5. That equals to 1 over something, right? Like whatever that something is. That something is my total resistance of the branches. Yeah.
Generally, I was like 13 over 14. The result will be 13. So for what all of this also here, it should be lesser than that. 85, you get 3. It should increase. If you get something higher, you calculate something wrong.
Yes.
It's easy to check.
I'm definitely mixing some things up.
Not the Google Docs latex, man.
It's for documentation purposes.
So, 1 over 2 is
Yeah.
5 eighths. 5 eighths.
Those online, are you following?
So because you can go
Oh,
one over plus one half is equals to that means R in this case.
Those online, are you able to follow? Hello? I didn't fucking unmute myself after your part, Joseph. I'm sure it's fine. Are y'all able to follow, guys? Anyone? Everyone okay?
Being high, I got a question.
Okay, yeah.
I don't know about I think this is one of those like isn't this post script? So like
Wait, sorry.
you know
What's the
qualification?
Yeah, so the
Present.
potential here.
There we go. Now I can see it.
So the always go downwards, right?
Because there's one coming the potential difference between this point is higher than that, so it always excludes that point.
That's right. So if there was like a battery here that has a potential difference this way, then it will start doing that, you know.
And then that's
And then that's where the funny is, you know.
Yeah.
So we'll briefly touch on that later. But the reality is that you simply shouldn't be designing circuits this way.
Yeah. Like, let's say whenever there's a short voltage, basically things are they should add up to 0. But then this seems like a loop, but it's the total of this is not like 0.
No, it's in fact because what you have to do is because you have a side positive and negative here. So for instance in this case, I try to so the voltage across this point, so that means measuring the voltage from the notice that this is so I define positive here, which means that the voltage across this is negative. But then the voltage across this is positive, so it cancels out. Yeah. So the sign thing,
Yeah, but then we are supposed to make work
Just now.
it doesn't
When it's 6 p.m. it doesn't work. Yeah, I've been contacting this now, but like, you know, I tried to set up for the sitting, but then one of the set up like, you like fine.
Yeah, usually I keep my level
Yes,
11 p.m.
Yeah, I did.
Yeah. It works before.
Let's say that, you know,
unfortunately, like basically the entire game.
there's another potential difference.
So I can't do anything about it.
Another cancels and stuff.
If you guys pass your trading service,
Because I think this one is something that always makes me up. So
in fact, when you consider this loop, this voltage, it's not relevant. So, yeah. You're right.
this one comes up.
You're right.
This is interesting.
That also is getting disposed of, so you get it by yeah.
So this one
Yeah, which one is the annoying one because that's where you have to multiple sources. Right, yeah.
So this one right now is the 4 plus 8 over 5. 1.6. 1.6. So 4 plus 1.6.
That's a new.
That's so basically we merge this. Find out the solver. So 1 over the amount.
No scientific application. I got one.
I just do the political.
Oh.
That's very good. It's very good at that because I'm very to the ceiling in my house. It's like, so I got a lot of things very close to the bottoms of my shelves. A lot of like, bad culture, my brother-in-law.
Try to remember.
Yeah, I remember that number, you're the right.
Huh? Really?
What's on the board?
This is already actually a 199.
If you want to do question, just leave it for 5.
I mean, that's
Wait, what's the question? What are we supposed to find?
Just get the total, what's it current?
A current, okay.
The current true low circuit. Yeah.
Thank goodness I remembered this. Otherwise, I would have pain trying to figure out which of the 7 is 1.81.
Yeah, but so this one is
Once you get there, you just buy.
Yeah. We just need to
I equals B hat. So 5 over
equals
total resistance.
okay.
Oh, yeah, sure. So, okay, so the first thing is arrange it into a less painful shape. That's always the first thing to do. So, start with where potential goes. Let's start with potential. Yeah, so start with the energy. So, right, so the start to destroy something on the base there, right? You have to do something to all these kind of things. It's
What answer do you want to this?
Yeah,
135/112.
So now
Wait, what do you resolve first?
Yeah.
So
Do you resolve the 8 and 2 first?
Yeah.
Eh?
Yeah.
Okay, I got that. Plus 4, you get 5.6, right?
Yeah.
Over 5, yeah.
Then here is just 16.
16, correct.
Then you combine the two. Oh,
You combine
I
wrongly.
combine them, yeah.
You do reciprocal.
Yeah.
You got it?
So I'm
Oh, so
yeah, it's about.
About that can really.
No, I remember the answer. I just don't remember in fraction form.
Oh,
It should be about that. Yeah, that should be correct.
then whatever it is.
Yes, my mathematical skills.
It's so true. It's so true.
So you found what? What have you found? You have the resistance of this.
Yeah.
So then therefore you have the resistance of the whole thing. Yes.
Yeah.
Right. So then
This is 16.
yeah, so then you can get the reciprocal like this, find the total resistance of the whole shebang, right?
What's the voltage?
Right. And now so now you have the current here.
Yeah.
Right.
Yeah.
So then what's the current like here?
Oh. So you have to. Right.
How would you find that? I'm gonna find everything.
Oh, you have.
I mean, I ask you since I'm gonna find it.
So that's
So like, you're done, you might as well. What's the current at this point?
What this point? I'm sending you, bro. I think white tees.
as water.
Such a Sam thing to do. I love Sam so much. Yeah.
Over here.
Mm-hmm.
Or you can imagine it like.
You know the Christmas tree downstairs looks so big now.
It's the Christmas tree.
It's a Christmas tree right downstairs.
It's always one.
Yeah, it's always something like
Where's the Christmas tree?
in this room.
It's right.
Like right in the middle.
I never go in there, so I don't know.
Like it's walk when you walk on there now, and that's how it's pretty.
It was not on.
That's very.
Oh shit. I wanted to like pull a reference from there. It's such a sad scene. And then the same Christmas tree set up.
Every SAO reference sound has not ended well.
Depends. Season 1 will end well. Anything after that will not end well. Season 1 Christmas episode was so fucked, bro. His entire team just died. Then he's like traumatized. Traumatized as fuck. Lovely.
You should have been there the other day. You watch No Game.
I don't want to watch it. I actively avoid the show.
Oh, okay. We watched. There's no season 2. Yeah, there's no season 2. But it was so peak. We watched it in the classroom. Like 8 projectors.
Oh, I just finished watching Kaiju number 8. I watched like one season in one night, second season the next night. It's so good, bro. It's funny when it needs to be, but serious when it needs to be. Goated. It's like I'm sorry. It tries to be serious, but the main character is so.
Okay. I get the idea. I get
People die, but it's funny. Think along the lines of Attack on Titan.
if I could
Wait, this works really? Yeah, we already done this.
I mean, we basically know that it's one. So, we know that this area, so the top is 20 or 5. So that's definitely wrong.
Yeah.
Yeah, sorry, I think, yeah.
Because like all you did, if there's a 5 that after table 9, because 5 goes right, then we also 5.
Yeah, that's right, yes, yeah, you did already. But to be clear, so it's like, when you analyze this, but you are, so you can. This is really, or I. Yeah, it's 28 or what? Yeah. Okay. Yeah.
Because it's 20 years.
Yes. So you have to draw it. So that's easy. It's not this, but it's not about. If you come back in 2 weeks, you understand. 2 weeks. Right, yeah. So it's not about this. If I try to find
the balance is 3.5, the rest will just low. Then you can also be something similar.
Which is, okay, that's just a thing. What, I just between one word again. So we can. Yeah.
That's the most.
Okay, is everyone feeling comfortable with the state that they're in?
This is the fraction of 7.
I'm pretty sure there's no 7s, but okay.
No, this is the fraction of 7.
This is
0.857, and then the repeating is 1.
the current for parallel. Wait, no, the voltage should be the same.
It is
Between 2 branches, yes.
Between the branches, yes.
This is 3 of 7.
So it should just be 5, is it?
The voltage across that branch
Yeah.
will not be 5 because there's a 4 at the top, right?
This one is 5.
Feels
So I'm not correct.
Yeah, it just take it out.
Oh, it's a voltage.
Because of that 4 up there.
Because of that.
There's a voltage across that 4.
Yeah.
So you can imagine as current flows through this resistor, there will be a voltage drop here.
So this
Oh,
one.
because it's.
So the voltage will drop.
Basically A of.
So what's the voltage drop right now across that resistor?
Okay.
Yeah.
So
Wasn't there a voltage drop from the other one also? The
Yeah,
first side?
so.
Yes,
assume that we
yes.
have this one.
Yes.
In fact, this is just 2.5.
Just half of it.
This will be.
This is just
So we just
2.5.
divvy up.
Just half. So this is just 4 over the total. It starts 5.
Yeah, this.
No, there's no over the total. You find the current through the resistor,
Yeah.
then you have IR already, right?
Wait, you're finding current?
Like because you have to.
No, your current is the
I
same
know it.
floor, right?
The current
Oh,
it's
it's
the same as like- as the
Voltage is the same floor.
current here is the same as current here.
Yeah, yeah.
But current here is current here, not the same as current here, correct? The sum of these two.
Otherwise, this would actually.
Yeah,
correct.
be one out.
So I have the current through this and I have this resistance. What's the voltage drop across this?
Yeah,
All over the total of this. Times 5.
yeah.
The voltage drop. What is
I mean,
it?
I'm rearranging the math, but correct, essentially.
Because it's a
Yes,
voltage
yes,
drop.
yes, yes. So,
Yes.
yes, so you have this voltage drop, and then now you can get the voltage across the front, which is simply 5 minus this voltage drop.
Oh,
Right.
then it should add up.
Because we know that.
Yeah, this should add up to 5.
Voltage
Because of this and this, okay, yes.
Okay, I feel.
Oh, wait. Okay,
Yeah,
that's 5.
yeah.
Oh, okay. So we.
I think in parallel is the same, right?
Voltage in. Yes. voltage.
Yeah, there are a lot of shortcuts here.
Correct,
There
and
are
parallel some-
a lot of shortcuts. So this is like
Current
2.5.
parallel.
This one is state divided. Because this is.
Okay, guys, I'm going to go through.
Oh, 2.5. Okay.
Go sit down, sit down. I'm gonna go through myself. Yes. What have you done to the projector?
Picking up.
He has molested it.
How am I supposed to live like this, Ray?
Where's the menu?
Ray, no. Oh, okay. Okay, so for those who have tried, here are the answers. Yeah, okay, I'm going to work through it on the board slowly. I'm going to, Joel, you want a picture of your working?
Okay.
Actually, Ray's camera is doing it already. It should be okay.
Yeah, but base camera is like.
Yeah, but my camera also starts because I have an aftershock laptop.
Yeah, see it.
Okay, it works. Okay, so we start by finding the voltage, by finding the resistance of this system here. All right. The reason why we choose this is because this is the only one with absolutely nothing in it. So we have 1/8 plus 1/2 equals 1/RT, right? So this 1/8, 1/2, this is 5/8 equals 1/RT. So therefore we have RT equals 8/5 ohms. This is so I have 8/5 ohms as a resistance of this entire circuit. Now I can take this whole thing and I can reduce it to I can basically just do this and then just get rid of this. Okay, I can do that. All right. So now I say, what is the voltage across this branch and this branch? All right. So this is 5 volts across and this is 5 volts across. I struggle with technology. What can I say? Okay, so total resistance is 4 plus 8/5. This is 28/5 resistance. So the total resistance of this is 28/5. So I can put this here and I can put this is 28/5 and I can get rid of this, right? Quite a bit nicer. This is just 28/5, right? So now I have 5 volts across 28/5 resistance. It's very easy to find the current through this branch now. I just say that it's what? V equals to IR, right? So 5 equals 28/5 of I. Yeah, I move everything over 25 over 28 by being retarded. Correct, right, Joseph?
The current passing through that. is
Yeah.
35. 0.5.
Yeah, so what did my answer say? I forgot also. Yeah, 0.89, correct. All right, so yes. All right, so this is my current through this branch. What's my current through the other branch? My total resistance is 16, so I have 5 over 16 equals I, right? So this is 0.3125, like Samia managed to find. So I have 5 16s and I have 25 over 28. I can sum these up and I can get my total resistance at the top. All right. So I can either do this or I can find the resistance of everything and then figure out everything as a whole. Okay. So what I've done is I've found the current through each branch, but I can also measure the resistance of the entire system. So I'm going to go back a few steps because I want to show you the other way of doing it. Both ways are equally valid. And I'm more comfortable finding the resistance first actually. But it's totally up to preference. So here we are. What's this? 8, 2, and 4. Okay, so again, we have the total resistance here. This is 28 over 5, right? We have the total resistance here. This is 16. So now I have 1 over RT. RT is the resistance of the entire system now. So I have the reciprocal of 16, which is the first branch, and the reciprocal of this 28 over 5, 1 over 28 over 5. This is 1 over 16 plus 5 over 28. And then I'm not calculating this on the spot, but I got 4.15. I got 27 over 112. Therefore, RT is the reciprocal of this 112 over 27. Okay, which is like 4.15. About there. We are converting to decimals now. Okay, so if you look at my answers, they don't quite add up. Rounding error. Okay, so all right, so I have 4.15 R for the whole system. And then I can find current through it very easily. So V equals to IR. So I have 5 across the whole system, and I have a current of 4, and I have I. So I equals 5 over 4.15 should be about 1.2. Okay? Yeah, 1.2. All right? So my I here is 1.2 amps. Now, if I wanted to, I can go further and I can measure the potential difference and current through every single component. So here and here, these two are the same. So each takes half of the potential difference across it. So this is 2.5 volt and 2.5 volt, which means here's 5 volt, right? 5 volt. Here's 2.5 volt. We know that there's 5/16 amps through this, right? Okay, then if I wanted to, I can find the voltage across this. So I know that there's 1.2 amps going through here, but that ends at this node. At this point, we don't know what there is. But we know that there's 5 volts here, right? So I know that there's 5 volts here. And what's my current through this? I have to find the resistance of this branch, which was 28 over 5. So then I have current through this point. This is 5. Okay, V equals to IR. I have 5 equals 28 over 5 I. Oh my God, I just wrote V again. Right, so then I have 25 over 28 again, right? This is my I. So I've got 25 over 28 I through this. Then I can find the voltage across this point, across this resistor. That means I can find the voltage across this resistor and I can find like individual currents through here if I wish to do so. Okay, so that should cover everything that everyone was trying to do. Any questions? Everyone happy? All good? Okay, great. Okay, so this is like probably the most complicated thing you will have to do if you're designing like most circuits, because most circuits, all the complexity is abstracted away inside the microcontroller. So no problem. Okay. And if you don't know what I mean, just forget I said anything. Because I'll teach you later. All right. So if you can understand this, great. Your circuit will not catch fire. That's all. Okay. Okay, now we're going to talk about Kirchhoff's, some examples of Kirchhoff's law. Joseph will take this. Yeah. Okay.
So I'm not gonna ask you guys to do this. So I'll just work them out on the spot. And so let's just start out with the current law first. Because current law is quite simple.
Which the white box was hard mounted to the floor. It's not even mounted to the floor properly, so one leg.
Yeah, it's just one leg and one wheel. Okay.
And sign up for the what's it called?
Okay,
The
so
Paralympics.
for the bike, let's look at the bike. The bike circuit first. This uses control current, you know. And so current in, so there's like, let me just draw this. I1
Those are the bottom there.
4 amps. Coming out here,
Let's see this
we
is
got 1 amp. Then you got 2 here, 3 amps. And you got, we want to find I4. 2 amps here. So current law states that. Okay. So let's identify which is going into the circuit. So you got I1, which is going in, and I4, which is going in. So that's in the left-hand side. You can do it the other way also. Okay, I1 plus I4 is equal to the current going out of the node. So actually you can treat these two nodes as one node because they're just be arranged differently.
Like they're shorted together by ideal wires.
Yeah.
So like they might as well be the same point.
So like there's nothing here unless there's a resistor here, but all the wires are ideal, which means there's no resistance between them.
Next lesson we will talk about unideal wires. It's terrible. Yes. Yes. I love unideal wires.
So equals to I5 plus, for label this I3. I3. So we just 4 plus I4 equals to 1 plus 3. Yeah, algebra. Then you can just solve. Yeah, I4 is equal to it's 2 amps. Wow. Okay. Next is
Everyone understands this, right?
2 amps.
You have in and you have out, and you must be safe. That's it. Yeah. Yeah.
Next is so start out in the back. So the trick with KVL when you're doing it is the battery, the longer wire, the longer side of the battery in the symbol is always the positive. And so now you imagine the current flowing through the circuit with this voltage source. You imagine the current flowing through here. So since the current is flowing through here, this will be positive. And likewise here, since the current will flow through here. So you just imagine like it's flowing in this direction because of positive voltage. And whenever current flows through this resistor, the voltage will drop. So that's why some textbooks notate it as we put an arrow here, which means the potential difference with respect to this point at this point. That is the potential difference. Yeah. So they're different notation. But I'll just write the equation down, then you can solve it. So let's label these one. And then I'll start off at this point. So you just go through the circuit. Take note of the label. negative 45.
He started from that point.
So I started from this point.
That's where zero goes.
You can start from any point you want also.
Yeah.
So in fact, if I start from this point, yeah, then let's start with this point. So negative 45, then plus the voltage across this point, which is V equals IR. So let's label the total current as I times R1 plus I times R2 here, plus because I'm going from here, then plus I R3. So this is equal to 0. So that is your, this is your Kirchhoff voltage law equation. Then you can just substitute in and find out what I is. That's basically KVL for simple circuit. Example.
Everyone's okay with this, right?
Yeah.
Yeah.
So in fact, you don't even need to use KVL for this, because you can just calculate R effective, and you just get. In fact, you factorize I out, you get R effective. R effect, the total resistance. Yeah. What can do completely? Okay, so for this next circuit, there's 2 loops. I'm just gonna write down the equations for them. So this.
The wiggly line is just another way to draw a resistor. It's a little bit slightly more correct way to draw a resistor. So in the software that I use to design circuits, the resistor is just a box, right? And everyone understands that that's a resistor. But wiggly line is like, I guess it's more correct. Whatever.
Yeah.
We label the thing R anyway, so like we know it's a resistor. But you can put wiggly line also, people will know what I mean. Okay, it's a resistor.
Oh. So here we got 2 equations. Okay, you can calculate this loop, and you can calculate the outer loop. So like this whole loop, like does it make sense to calculate this loop? Yes, it does. But then you would have to, because we know this voltage is 3 volts. So when I circuit, when you calculate this loop, it doesn't really make sense, because if you got lesser unknowns, it will be better. So when doing this circuit, it makes more sense to use the outer loop instead of this loop. So up from here, put your plus minus, and you can imagine the current flowing. And then just write the equation down, starting from this point. Maybe 3 plus, let's label this as I, and 1. Over this as I. I'll write down the loop equations first. So
Just to jump in, right?
I1.
For the previous example, I was the same throughout every resistor. So just put I. Now the I is different every single time, so we have to put I1, I2, I3. Okay. Yeah.
This is 15I2 equals 0, and negative 3 plus 10I1 plus 20I2 plus 15I3. So you notice this equation has 3 unknowns now. So you can see analyzing this would be more complex. But so with just this information is not, you won't be able to solve. You still need to add KCL, which is called Kirchhoff current law, which states that at this point, I1 is equal to, so this is I3. This is I1, I2, I3. So current in is equal to current out. So current in I1 is equal to current out I2 plus I3. So once you solve these equations, you can calculate all the currents, and using Ohm's law, you can calculate the voltages of course each. Okay, so the next example is superposition theorem, which
Okay, so the examples that we show so far, the three examples of KVL and KCL, if you wanted to, you can solve them the way that we thought earlier with basically just Ohm's law. Because like the KVL and KCL here is kind of like whatever, you know. Maybe this one a bit less. But for superposition theorem, where you have multiple current source, that's where like KVL and KCL really starts to like
required.
yeah, that's really required now. Then you really have to do the simultaneous equation thing. Okay. But we just want to express the caveat that although this is like hard and like looks important, in reality, right, if you see a circuit that looks like this, the guy shouldn't have designed the circuit this way. The circuit should not have multiple current sources or power sources most of the time. Okay, so generally your thing will have one power source or one voltage source, and then that's it. And you don't need this loop bullshit. Okay, so we'll show you what this is, but we want to be clear that although this seems interesting and important, it's not usually required for circuit design. And when you do find out that you need it, just learn on the spot again. It's okay. Yeah.
Next. So let's say I use a different symbol for voltage source. So in some textbooks you'll see this also.
Some people say too dark.
Yes. So for this, use superposition. How to use superposition theorem? So we consider this voltage source first. Let's consider this voltage source. I'll label it V1. So let's consider V1 first. And when we consider this source first, and whenever you're using superposition theorem, all the other voltage sources must be replaced with a short circuit. So you redraw the circuit with just a short circuit. So then you can just do your write down your loop equations for this. It's just V10 equals to 1. Negative 10 plus minus plus 20 I1
This month.
right.
I don't know. It's already connected. It's like you can see it from the screen. It's a lot better. Okay. How do I?
In fact, you don't even need to use KVL and KCL for this case. Like, you can just find all the currents, and the superposition theorem just basically states that you can add the currents. You can add the currents individually. Okay, so for this voltage one, I1, you can calculate it. Let's just do it KVL.
Yeah, that's the correct way.
That's the correct way.
Yeah,
basically.
the other way is just harder.
So this is one. The outcome. Then for the other circuit, you just do the same thing. And you calculate all the terms. For the other circuit. So this is
Get on this start box.
yes, you're right. Okay, so here's the I taught you that you're supposed to put when column flow this way, right, you're supposed to put plus minus here, but you have to retain the signs here because you already assigned them. In fact, you can actually assign any arbitrary sign if you want, but it is
Basically, you are assigning yourself a convention which you need to follow for the rest of the problem.
yeah.
Yeah, if you change convention halfway, everything is cooked. Yeah.
Like forces you decide what's positive, what's negative.
Yes,
Yeah.
correct.
Yes. So uh V2 is to get nothing from here is plus minus 5 minus 50 I3 minus 20 I1 plus 0 minus 5 2 1. Sorry. 30 is quite also. This part. What is this?
Wait, for the 10, why is it? Why is the plus on top?
Sure.
For that 10 ohm resistor, not the other one on the right.
Sure.
There is the what is the positive polarity on top?
Because I have to follow this.
Oh, okay.
I cannot.
You cannot change it. You
Yeah,
just
cannot
changing.
change it.
Ah,
I must follow this on the left side. So yeah. So once you get like
so what will be plus 10 instead of minus 10? The second equation, minus 5 minus 50 I2 plus 10 I3, right?
yes. Yes. Yeah. And Okay, so the reason, right, you're right. So the more technical reason, right, is the direction of the current that you set also. So since the direction of the current is so this I2, right? Wait, let me I'll draw here better so you can see. So this I1, right? Since current is flowing into here, this must be a plus. If you set I1 to reverse sign, then this has to swap sign already. So that's why this has the polarity of this has remained the same. So in fact, right, here I2 is pointing in. So this would be negative. So the more technical reason is the polarity of this resistor should be set based on the direction of the current that you set also. Yeah. So this is important. Yeah.
Anyway, if you choose the direction of current wrong, doesn't matter also. The physics does not change, correct? You'll get a negative current across the resistor, and like you will know that the your current direction is wrong.
So it's actually after we solve it, it's possible that we get a negative number. That means
If
that
you make a
the
mistake.
direction is
Yes,
the opposite of that.
yes, that's right.
Yeah.
Yeah.
Well,
That's correct,
it
yes.
could be confusing in circuits lah. Yeah, so you really have to it's like with physics, the free body diagrams, you have to stick with convention like X, Y, and Z. Yeah. So
No, it's correct.
it's like because current is flowing from the top. So whenever current is flowing through here, the voltage must drop. The voltage must drop. So that's why this when I start off here is negative. When it equals 0, in fact, when I bring over to the other side, this is 5, right? I start off from here. So when I start from here, I can say that I start off at ground, right? So this is 0. I set this to 0. Then when I go up here, this is 5 volts. That is not perfect, but like, yeah, it's a bit confusing, but as long as you follow the convention that current goes in for resistors lah, current goes in, you must put the positive sign when current goes in. Yeah.
And the way that you know what the current direction should be is you look at the potential difference at each point. So when potential difference goes from high to low, you know that the current must go from.
So if
from high to low, right? Yeah.
if you ever do this is wrong. Do not do this. If this is negative, this is positive. If you do this for KVL, this is invalid lah. Yeah. So yeah, these are the equations for this example. Yeah, that's it.
Yeah, so then you'll take this whole system.
Whole system of equation and just solve it.
How do you superposition them?
Okay, so once you find the current for when analyzing this circuit, you just add them up together. So let's say I1, I find it to be 1 amp, and here I1, I find it to be 2 amps. So the effective the actual I1 would be 2 plus 1, which is 3. So that's how superposition works, basically. Yeah. It's very tedious. Like I've been doing this for like doing this as practice for a few months when studying electronics. It's not, yeah.
Yeah, but anyway, this only applies when you have multiple power supplies. So
Yeah.
again, like what he says, you evaluate each one of them individually. Everyone else is considered a short. Then you add everything back
But
together.
not really relevant for PCB design.
Yeah, just don't design the circuit that way. Yeah, okay. So this is, if you see someone else's circuit, they did this. The first thing you do is slap them. The second thing is this. Okay? Okay, Kat. What's next?
Yeah, so this one is basically the same.
What do you mean under it?
So for this circuit, we got a current source instead of a voltage source. And so with current sources, all you have to remember is instead of shorting it, you replace it with an open circuit. That's all. Yeah. And you know the current here lah. So basically you know the current here, which is 6 amps. Yeah. So whenever you're doing this sort of circuits, you always label everything first, and then you can solve individually. Yeah, that's all.
Okay, does anyone have any questions?
What does the 6 amps represent?
Is the current, so that's a current source instead of voltage source.
So normally we have voltage
Yes.
sources, right? So,
Yes.
so batteries are voltage sources. Like most things are voltage sources. But you can also have a current source. So a current source is basically it's for now you consider it to be magic. Okay, it is something which somehow produces a constant current, not a constant voltage. Okay, this is a current source. This box over here.
So
Okay.
you can just set a constant current here,
Yeah,
like
and
at 2 ends.
it will vary the potential across itself in order to achieve a constant current.
Yeah, but it uses some magic inside to do that.
Yeah, the magic is
Nothing
really-
like this in real life.
Yeah, the magic is really like nobody understand the magic, okay? So don't bother. It's magic current source and that's it. Okay. So sometimes you will see this in, I've never seen this personally, but sometimes you can see this in the circuit. Yeah.
Yeah. So that's pretty much it lah.
Yeah.
So across that component, there's no potential difference.
There is a potential difference which you don't care about. You only
Oh,
care about
okay,
the fact
okay,
that it
okay.
provides a constant current.
Yeah.
Yeah.
Okay.
Yeah.
Open.
That's all.
Okay. Now we are going to do hands-on. So we are going to show you how to build a basic LED circuit out of a breadboard and like basic components which we have brought from like house or whatever. And then I will show you how to measure stuff across it with multimeter. Okay. So this is designing and measuring your circuit in real life now. No more math. Okay. So I'll show you what the circuit looks like and then you'll build it. Okay. It's my mouse here. My mouse is on the other. Okay, so here's my software which I use for PC, which I use for design. Okay, so we're going to cancel. Yes, I do. You are absolutely right. Where the hell is my KiCad? Is it not shareable? Okay, I just share my whole screen. Okay, great. So we are going to light up an LED. Okay, so here is an LED and I have a resistor. My resistor is of some whatever size. I think I have 10 kilo ohm resistor. Okay, so 10K means 10,000 K means 1,000. Okay, you might sometimes also see M, which is mega. So big M is mega, and then you also have small m, which is milli. Okay, in this case, I have 10 kilo ohm resistors lying around. So we're going to make this. Okay, so it's a LED and a resistor. Okay, then I have 0.5 volts. Okay, they don't have a default. Okay, so I have 1.5 volts across my resistor and LED. And then I have a ground here. Okay. So this is my circuit that this is the circuit that we are all going to build today. All right. So we need this because the LED has a maximum voltage across it. Actually, 1.5 volt is quite safe, but okay, so LEDs usually can have up to like 3 volts across it, okay? So if I change this resistance, then I will have a different voltage across the LED, which will make it heat up more or less depending on whether I increase or decrease the voltage. I am counting? Why?
Because LED has a fixed voltage.
Yeah, fixed voltage drop, right? But then if I but I reduce the voltage drop, I reduce the brightness. No?
Of course, the LED.
Oh crap, he's right. So it's just not going to turn on then.
Oh, okay. So basically, current has to go through the LED before it starts turning on.
Right, so I'm
Yes.
changing the current, not the voltage.
Yes.
Which means that I cannot run it on a single AA,
Okay,
right?
Basically, a diode which has a 4 voltage.
Right, so I'm wrong. Yes, correct. So then that means that we have to drive the thing with like 2 or 3 AA, correct? In series. But I have to achieve the forward voltage, what? I don't know what my LED is.
Well, some LEDs are 0. Oh, wait, yeah.
Right. Okay. So for the I'm gonna change this to 3 volts. Okay, so we're using AA batteries, which we have conveniently soldered wires directly onto. Do not do that. So then I have 3 volts and ground. All right, so I have a 3 volt potential difference across this system. So this is what we call a current limiting resistor. This is one of the like actual applications of like why we need to do V equals to IR. So let's say for argument's sake that this has a 2.5 volt drop across it. So this is the voltage that the LED expects across it, okay? So I need to find some R value here such that there is 0.5 volts across this. So I would V equals to IR this, and then I would figure out that this is, I don't know, some number, all right? Depends on the resistance of the LED. And then I would be able to show that, look, I've got 2.5 volts across this LED, no problem. It's not going to blow up, okay? Then after that, you have to check what is the current through the LED. So if actually, what do we do if the current is too high? We just increase the resistance, right? No choice. And then the voltage drop will be greater. Then we're not running the voltage. Then we're not running it at max voltage, what? Let's.
The voltage across the LED is assuming to be fixed.
Oh, right, because it's a diode. It does not have a flat curve.
Yeah.
Okay, diodes are magic. We'll talk about it next lesson. But basically, no matter what you put across the diode, it expects that voltage. So even when I change this resistance, the voltage across this will still be 2.5. So I can increase this resistance to increase the resistance of the entire circuit. That changes the current through the thing. And the current through the diode is what changes the brightness. Okay? Okay, does that make sense? I kind of fucked up like twice there, but it makes sense now, right? Yes, so current affects the brightness, not voltage. The voltage across the diode is more or less constant. Some
is in the data sheet.
Yeah,
Usually 1.7.
because diodes are some magic component that we haven't thought about yet.
Exactly.
Diodes do not behave in like normal ways. There's a lot of things that don't behave like in the ways that we have described so far. We have thought about basic resistors so far.
That is a non-ohmic.
It doesn't follow Ohm's law. It's non-ohmic. Okay. So most things are just resistors and they don't follow Ohm's law. Good. This is why Ohm's law is so important. But plenty of things don't follow Ohm's law also, like anything which is a semiconductor. So a semiconductor is like where I have a silicone, where I have a piece of silicon and I fill it with magic crystals. And then like now it is magic. Okay. And I refuse to explain any further. That is what a semiconductor is. Yeah. So in this case, LED is magic. It has a fixed voltage across it. No, does it? It does,
Yeah,
right?
yes.
It does, right?
Yes.
Yeah. It's that's what that curve is, right? Yeah. Okay, yeah.
How is that curve?
Yeah, the diode curve. Okay,
Like,
great. Yes. Okay, so we are going to put 10 kR here because that's what I have, and like we'll see what
Why
happens.
is it like that? Isn't it like the one that goes up?
Yes, you have the forward voltage and the breakdown voltage, correct?
This one, right? This is the one. Right?
Yeah. So here's the forward voltage. After that, it starts conducting.
Oh, okay.
Yeah. Show me the curve.
The-
See, so I apply this much voltage and then it starts to conduct.
Okay.
Yeah.
Okay, right. So there's a minimum voltage that it requires.
Yes. Okay, great. So this is what we're going to build. Come here. I have LEDs and stuff here. So whenever you have an LED, right? Where are the LEDs? Okay, so an LED has a long and a short leg. Okay, long is positive, right?
Long is positive.
Yeah. So the long leg is positive. So I have seen students. This is quite funny. I have seen students just take it. Oh, it's too long. Just click. Oh.
It's fine because
So
you
you
actually can look inside. If you look inside the diode, the smaller plate is always positive.
Can use a multimeter.
Yeah, you can use a multimeter.
Or a smaller thing.
Yes.
Or
The smaller plate.
The smaller plate.
the smaller plate is possible. And the longer length is
Okay, right. So
the smaller.
diodes are directional. You have to plug them in such that the positive and negative is correct. Okay, the positive leg must see a higher potential than the negative. If you try and put it in reverse, it will usually blow up. Okay. It's not very violent. It's just it just kind of like burn. Okay. Yeah. Okay. So not fire, right? It just fucking heats up and just stop working. Okay. So this is a breadboard. Where are my breadboards?
I handle them.
Or where's the one that has no backing? I want to show that one. I have one that has like no speaker. Yeah, but I need to show that, right?
Ah, yes.
Ah, yes. My beautiful mutilated breadboard. So okay, so this is a breadboard, okay? So this is what like amateurs use to design basic circuits. But no, at the end of the course, you will design PCBs, okay? Which is what like adults use. So all of these rods are where sockets are connected to each other. So you see all these sockets, any row of sockets is connected to all the other, like basically all the sockets in one row are connected, but rows are not connected to each other. Okay, so you can see here all the rows they're connected within themselves but not to each other. Okay, and then like I've also got this power line at the side, so plus and minus. So this is where I can put ground and like whatever high voltage I want to use. Okay, anything that's higher than ground. So I can plug things into the sockets, and I can wire things up this way, right? Because I can put like something here on this row and this row. Then I can put something here, this row and this row. And now these two things are connected, right? Here, because they're on the same row. So I can use this to wire together basic circuits. So breadboards are cool for like when you have like 5 or 10 components. But anything more than that, you start like this horrible mess of wires all over the place, which is why nobody likes breadboards. Okay, nevertheless, it's fine for what we're doing today. Okay, so make a circuit and then we'll multimeter it together. So this is a multimeter. Okay, multimeter is a magic box which tells you things about the circuit. Okay, so we've got these two probes here, and we can use it to put points about the circuit. All right. I'll talk more about this later. Let's build the circuit first. Okay. I have LEDs. I have jumper wires. Okay. So here are jumper wires. Might as well use a nice one. So these jumper wires are male to male. Okay. So you have male to male and female to female and male to female. So basically, female means there's a socket. Okay. So these are female wires. See? And the male can plug into the female like this. Okay. Breadboards are entirely female, so I can just plug male wires in like that. All right. Okay. So my breadboards are very cheap, so they're a bit hard to push in. Okay. All right. So we're using male to male wires today. All right, because everything is female here, and we are going to take my sisters, which are somewhere. I'll probably bring you.
You can use my camera, bring before the handle and stuff. Oh yeah, that's true. This is
Okay, you are going to find out what the resistance is, but they're not sorted.
This is
Okay.
very high. You see that?
If you want to, yeah, just here, these are
You see that?
resistors.
Very high.
Okay, so
Yeah.
resistors come in stacks in rows like this, okay, in tapes like this, and you just pull them out.
Okay, you can't take
And
it
you
out.
take this thing, you can bend the legs over.
That's how it's connected
like
to
this,
the Teams.
and you can just insert it into the breadboard. Okay.
Yeah, that's
Alright,
right.
so
Just like
you also have
being her
batteries.
next one.
So here are the batteries which Joseph has soldered. And this is what we do for the part of education. And you need to put 2 batteries in series. Otherwise, you're not going to have enough voltage. Okay? Okay. All happy? Okay, kind of try. Yeah. And don't put stuff on the water part. Yeah.
But it's true. There's no control. What the?
No shot. You cheated.
So you need two batteries.
Yes, you need two batteries in series. Otherwise, you're not going to have enough voltage to plug in. These semiconductors, so why does everything have to be so hard?
You guys want to see the curve of a diode?
Yeah, this one. This one, right?
Yeah, you just add them across. Yeah,
Yes.
fine. Yeah.
Hey, wait. There's a breakdown region. So here it goes. Poof.
Yeah.
Yeah, so breakdown region is when like basically what is the maximum negative voltage that the diode is able to block before it just dies. Yeah, and it just starts conducting anyway. Yeah. Yeah, liquid scarlet. Oh, my favorite, the liquid scarlet. Okay, diodes.
Wait.
Why does everything have to be so hard?
Electronics is like flashing. I think like the capacitance of the constant, it's not on that one.
So
Like you put the you don't put the resistor, the LED in.
wait, so just a minus of the diode, minus is the shorted to ground, correct?
Yeah.
And the other one is to the battery.
Pull out one.
Yeah.
Okay.
So there's a reason why we have a resistor in series with LEDs. Because you just short the battery
This
LED.
is ground, right? The lower.
This whole, so
Technically.
this one is for
By-
one
by-
line, another line like this.
Yeah, so the one closer to the middle part is always ground.
It doesn't matter. It's like they just shorted together. You normally we assign it like plus and minus, like by convention, but you don't have to follow that convention.
If I put the diode here, I cannot connect with the wire on top, right? It needs to be.
You have to bridge across another wire.
Okay. Alright, then. What should we about this thing?
Yeah, just tear off.
But it's all.
Just
Oh my God, that's amazing.
So the bed.
That's my job.
I do. I was my dad told me.
Let's just take one and.
Oh, yeah, so you actually can.
Yeah, the
Okay, so like the button, how to read it from my.
To the positive of the battery, and the positive on the diode is positive plus again, like it on the fiber.
Really? That's fine. Wait, who's in this? Is your in this?
Yeah.
Okay, I think you how to use it. I'm sorry.
Sorry.
Yeah, really. Yeah, I'm gonna do a multi-level.
The first thing you need to do is all get to know
Oh, down here, okay.
Yes.
like also.
We got a bunch of, the down says off, it's usually, when we do the J, one and goes to the.
Yeah.
But okay, so we do is this line of okay, I don't care what this is. This is for and actually, so this one here goes to DC.
This is the ground.
So this is DC world. Okay, where's the left?
Guys, now really something.
Oh, so it's not for that, it's not more. Okay. So the reason why I say this game here, you can talk about it quite a while, develop now. But now it's one of the ordinary like, you know, like then the approach to positive, right? It's not region. So, yeah,
Don't go on is positive, right? So I should connect this to the.
contact later.
Negative on the side. Then something on the side. Okay. And.
Yeah, so that's more like this, right? Because this is form of that was like this standard for it's already actually the first So I can measure the position across the space. You see minus 0.004 so it's a minus which I'm not mentioning actually values, right?
It's actually I need to
Yeah, 0.04. It's very small one, right? Okay, so this is a list of so then
that's the
so it is most prime. Now we are in O mode. Okay, the vessel that this is not really solution with that it will be supported conditions. Very low resistance section. It will be when it has continuity. This is diversible. So I propose as the force that's the polarity. So I can see if I click on this.
So this this is positive. This is negative. And this, I think we just put in
That's why like this is not how that it should be positive. That's very
so negative
you need log on capacity, right? The LED
just need to connect those.
negative, positive. So this this must be
But no, it's
so
very
we don't do contact
because this one is a positive. We have to positive, we have to go for positive in the this one also so I simply just find this why
yeah, you also need I think yeah,
so basically
if we start from positive, negative, positive, so because we start from positive, right?
For making a very very sorry, so I'm confused on the I mean, bring a working tap mode.
If it's a connection, then it was connected to a mode.
That's very enough of course, whatever you are. This was connected to but like any other. Yeah, okay. One way.
Yeah.
You can use a so you should very good
because I don't know inside of this.
It was full from the first step to full from step
the governing but young is for maybe minor
positive will always get on.
So the positive is out there.
Yeah. So
We
can just pick up the L and try
So if you think that you're not very and you have the result from that
plus, minus and equals.
it could be that. So we can okay, or will be the same over. Okay, so we are three choices not one convention. So it's very complicated.
So we just need to complete
this is really without use something so we put this in
The negative one
goes with the hyperlinked resistance. So that no current flows through it. Right? So an ideal emitter has zero, which is that it does not affect the current flow through it. Make sense? This is how we compare to make the problem all the other functions for we need to state computation.
Oh, the second one is
where do I
That makes sense. So about this current mode is low. That's the one is right. So if someone don't know and then I didn't have the chance, I need to be supported. Actually, so I got the cost my that so this is a computing cost. You have to try the only thing you have to have is
The function will not more sense. This is the red one of the digital, yeah. Okay, so you want to try using or not? Yeah. What try using or not? Yeah. So turn the down, turn the down into worse.
This is
This was also Florence. You know, try your voltage. You have some this is what this is magnitude of 120. So it's all film is correct as the lag. It'll be AC emissions. What that means is okay, so now we just want to see it's full less. Here's like no, you're in voltage mode now.
Oh, okay.
So the machine here to get a current as well.
So if I'm on volt, I'm checking for voltage here. It needs to be on voltage.
That's right.
Oh, okay.
Yeah. So for current mode, then I'm going to use that. I don't know why it's so difficult for multi-meter factor. There's just this is standard all multi-meter based feature. Yeah.
Because we don't know.
That's shocked.
Positive or yeah, but I'm going to be getting more
just one. Just
no, it just has to be released.
so that's why it's like
It's just my joystick.
I don't respond like
Okay, we should speak into the nature of it's even brand where most of
yeah, that one is
1.58 volt.
Whenever I hear the term blow up, I'm like just scared because
It's okay, I haven't voted as expected because it's still double. I just see it happening. My
I can get the voltage just across this resistor, 1.5 volts, expected also, because 1.5 volts plus 1.5 volts is 3. I can switch to resistance mode like this. So see the ohm symbol, this means that I'm in resistance mode. If I press select, then I can detect different things. This is continuity. It says, is there a short circuit or not? So for example, I can touch the same leg of the resistor.
Oh.
Now I know my resistor is not broken. Okay. This is more useful for like wires, you know, like this jumper. Can I trust this jumper? You continuity across it. Okay, this is diode test mode.
Okay.
So I can put a diode across it and see the diode lights up. And then this is a safe way for me to check the polarity of the diode usually. Okay. So I don't know if my diodes are fucked or what, but like they don't seem to want to work. Let's try. Yeah, it's not 21. I don't know why. Yeah, I think my diodes just cooked. Try Joseph's one.
Yes,
Yeah, they see. So the thing is lighting up. The thing is lighting up. If I do the other way, it doesn't light up.
Does it break?
No, it's running a small voltage. I don't really know exactly how it works. I just know that lights. Okay, so this is how the diode test mode works. I press select again. The F here stands for farad. So farad is the unit of capacitance. We'll learn about it next lesson. Okay, capacitors are like interesting, but they're not magic like semiconductors, so it's still okay. All right, we're back to ohm mode now. So now we can continue testing resistances. So let's find out the resistance of this resistor. What the fuck? What is your problem?
Does it have to be in the right
It's
position?
actually a zero. There's no way it's a 0 ohm resistor. What hell?
Take off first.
I think the magic of the LED is just making things harder.
Ah, there it is.
What's that? 100 kilo ohm. Okay, you can see how I've got intermittent contact, right?
Yeah.
This is, yeah, there we go. 10 kilo ohm. Yes. So 10K is quite a standard resistor size. So notice that like my probes are having intermittent contact, right? So like this will affect your measurements. So you need to have very, very good electrical contact with your probes against anything that you're measuring. Okay, yeah. I don't have a very deep understanding of LEDs, so I can't really explain why the hell I haven't been able to measure the LED so far. But like, I hope I can at least demonstrate multimeters to you. Okay, yeah. Okay. This is amp mode. So measuring microamps, milliamps, or amps. Okay, so you need to set to the correct range of sensitivity. And then you have to choose accordingly whether you want to have amps or milliamps or microamps. So let's say I want to measure amps, then I'll go here and I'm measuring some huge current. And it'll be less sensitive than if I measure milliamps or microamps. So when I do this, this is in current mode. Yeah, brighter. It's gonna burn, be careful. So never leave the thing in current mode because a current mode is a dead short because an ideal emitter has zero resistance. Okay. So if you just leave it like that, you'll leave. And then like someone comes, usually they measure voltage first. So then they're going to take the voltmeter. Ideal voltmeter has infinite resistance because you put it across. So you shouldn't have current going through the thing. So if you do this, if you leave it like this, it's a dead short. Someone's going to put this across their circuit and they're going to short their circuit. You're gonna have a crap ton of current. You're gonna have a crap ton of current going through this. This is not ideal. It will just blow up. So never leave this in voltage mode. In current mode. Always put it back to voltage mode. All right. Yeah. Okay. So a voltmeter goes in parallel across whatever you're measuring, and an ammeter goes in series with what you're measuring. Okay, because current is true, right? Yeah. Okay. So remember to choose the range. Remember to set the mode. That's all for multimeters. Everything else is like nobody cares. Okay. Yeah.
What's the difference between these two poles?
So this is for milliamps or microamps. So this has a lower max current than this, but it's got a higher sensitivity. So for this one, it's like less precision, but more amp, Yeah. So like it takes more current to fry this one. Yeah. So if you fry this, you have to go in and you replace the fuse, which is annoying. Yeah.
So essentially, if you want to use the emitter function, you just start from here first, then change the.
Yes, if you really don't know what range your amps are in, right, you start with this one first.
Start with this one and this mode, is it?
Yes, correct.
Oh, okay.
And then like you see what number you see, if you see like 0.001 or something, then you change to the more sensitive one. Yeah.
That's why I know how to make resistors that even work properly. We just line up all
That's why it's like, because I'm like,
in series, right? You make a resistor that allows us to control the lighting.
Like-
yes, they have a very great idea.
It's like
enough resistance, very low resistance. So, let's just see right now. Down.
Okay. Has everyone managed to make their circuits? Is everyone pleased with the result? Did it light up?
Yeah.
Okay. So
Can't see shit, bro.
Light up your life.
Okay. It will be more intuitive if you use the power supply. Then you can see the. Oh, it doesn't work.
Okay.
Never mind.
Sure.
I couldn't light up the diodes in series.
Joseph,
Maybe I have to need more.
Joseph is going to do a demonstration with the power supply. This is a DC variable power supply. It is a magic box which makes a voltage or current of your choosing. Okay, yeah. I cannot stress enough how magic this thing is. Like you look like the electronics inside, right? It's terrible. Yeah. Yeah.
does it have a microphone?
Dude, it's got everything inside. Like you have like the super clean DC signal with the amazing rectification and the smoothing, You have like the funny inductor and whatever.
You're putting it there.
Get mouse. Oh, you're putting two LEDs in series. I like that. Okay.
Detonator call.
Yeah.
To Bluetooth bit of light.
I mean, they should be first. We shouldn't select first then one.
That's right.
So with diodes, right? Okay, this is not part of our syllabus. I mean, not part of our lesson, but like with diodes, there's always a forward voltage drop. So right now, this is set to diode mode, which will measure the forward voltage of the diode, which is like the fixed voltage when diode allows current through, yes. So we measure the forward voltage to be 1.7 volts right now, and the green LED should be a bit lower or higher? Higher. 2.1 volts.
Yeah, how about the square?
Yes. So why is it higher? Because physics. Yes. Weight is low on the wavelength. Something to do with that. Yeah.
This is a lot higher, is it?
Yes, a lot higher. Like 2.1
Okay.
versus 1.7. Yeah.
Not the square one, because it lights up less, right? So
I think 1.7 also. I think it's too
No, the square wave LED is 1.5.
there's no,
But it's like barely any.
yeah, barely any lights, right?
I don't know why, but like.
Fuck LED. Yeah.
Okay, so right now so we know this is 2.1 and this is 1.7. So let's turn on the bulb, right? And let's take a look. Okay, let's not blow it up. Okay, let's set this to 5 volts. Nice number. Oh shit. Okay. 5 volts. 5.8. Okay, 5 volts. I'm just gonna leave the amps constant because we are going to supply a constant voltage. If you want to yeah. Okay. So at 5 volts, it's not where it lights up. Okay, let's reduce the voltage to peak. Okay, wait. Let's connect the ammeter. Okay, so I'll demonstrate how to use the multimeter in the ammeter mode. So since you're measuring small currents, use MA. There's you can see like there is the maximum current it can support. So this is 1 amp max. This is 20 amps. So you can measure a lot of current. We are not doing with 20 amps in electronics, man. Yeah. Okay.
So the other one is the amps, right?
Sure.
The dizzy ones are if you have like high amperage rate.
No, even if 1 amp goes through you at 240 volts, that is deadly. Deadly. Yeah.
From the body.
So it's the voltage.
actually
1 amp is huge. 1 amp is huge.
Like that LED at max brightness probably like 20 milliamps. You know?
Yeah.
It's really 1 amp is like
Yeah.
What I'm scared.
Ammeter.
Basically, the amperage is what kills.
no, it's not that simple.
It's not that
Because the
simple.
resistance of
There's like the skin effect or something. I don't know.
Yeah, so
this is
quite fun. Don't think about it. Just don't touch it.
Yeah, I'm not gonna think about it anymore.
Yeah. This is not ideal.
It doesn't click.
I'm just gonna hold it and like someone. Okay, so you can see it's 4.5 milliamps, right? Can someone change the voltage for that?
Press the knob to change the significant figure and then turn the knob.
To
Yeah.
what do you
Yeah.
want? Like increase, okay? Decrease?
Change it below. Change it like slowly reduce it. So you can see as we approach
Actually
the forward voltage, which is as we calculate, there's 2 diodes in series. So it's 1.7 plus 2.1, which is 3.8. 3.8. You see, right now it's 0. Right now the amperage is very small. Why? Because there's 0.2 volts across that resistor. And the resistor is 2.2K. So you can calculate.
I see.
Sorry. So you can see as you approach, like put it at 3.8. Put it at 3.8.
I see, right?
Yeah. See, now it's very little. And see, I go even lower, it's gone already.
No, it's
No, I
resistant.
Yeah.
Oh, okay.
Oh,
So you can see it's gone already. So right now there's 0 current because this is not enough to overcome the forward voltage. So that's like that's the thing about diodes lah.
Interesting.
that's the graph.
And okay, so let's go back to
3.8.
so now let's measure the voltage across the diode as we increase the voltage there. So right now it's measuring the voltage.
Is it in?
Okay, so now I see 3.7. Increase it, no?
Oh, sorry.
But you see, it's like
It's still kind of consistent, right?
it's consistent at. I don't know why is it big?
See there. No, I think because my voltage is very low. Yes.
Yeah. See 3.8, 3.9. It does vary, it does vary, but you can see once it hits that point, even a large increase in voltage is very minimal increase in voltage across the is so you just assume
Why is it so
it's-
though?
Huh?
Why is it so?
Because of that graph.
The diagram.
The diagram. Yes.
It's okay. It's honestly it's okay unless you are specifically building an LED driver circuit. This does not matter. You just care about light up or not because you care about the
Yeah.
LED. As
So actually, most of the time we just treat things or chips or LEDs as black boxes.
yeah, which means we don't care what's inside. We just care about how it behaves.
How it behaves.
Yeah.
Yeah.
Okay. So, anyone happy with this?
Yes.
Okay, we have a little bit more to cover and then we're done. What time is it? I have time on this part.
Then what's the other?
Yeah.
Which one?
We didn't make like okay, we didn't make slides for AC and DC because we don't need to. Where's the duster? Oh, we need duster again.
Yeah.
Oh, where's the marker? Big camera for that.
No, it's just more wireless. But then there's no one, so
Yeah.
It's okay, I'll post for you.
Where's the green marker? This one's quite. Yeah.
Yeah.
What? Really go. Now I have to find the marker.
Isn't it?
Green one.
I think this has enough. Yeah, it's like
I guess we'll find out then. Okay, so let's talk about AC versus DC now. So AC and DC stands for alternating current and direct current. Okay. So direct current means that the current direction is always the same. The voltage necessarily, but the direction is the same. Alternating current means the current is changing over time. It's changing direction over time. Okay. So the most common alternating current that you are going to see is wall power. So it is by default a sine wave like this. With an amplitude. Is it amplitude or RMS? Amplitude, right?
wall
Wall voltage.
measuring is RMS.
So RMS 230.
RMS is equal to 230.
Yeah.
So the peak is higher.
Okay, great. So basically, what I was discussing with Joseph just now is the root mean square voltage. Nobody cares how to calculate root mean square voltage. Just Google it when you need it. Okay. But basically, it is a sine wave of voltage against time. So here is voltage and here is time. All right. So the voltage will peak and then come back down to zero, then switch direction. Okay, so this is alternating current. And usually from wall power, it's like 50 or 60 hertz of period of the sine wave. And the root mean square voltage is 230. Root mean square basically is kind of like average, but not really. Okay, it's kind of the average magnitude of the voltage. Okay, good enough for people to know. 230 volts hurts like hell when you touch it, so don't touch it. You can die. All right. So DC current, on the other hand, is just going to be a flat wave, like flat line like that usually. Okay, some voltage, which is usually when we measure it, is positive, right? So this will not change direction. If it changes magnitude, sure, as long as it doesn't change direction, it's still direct current. All right. that distinction is not that important, honestly. What matters is that the AC current to DC current, how do we make it stop changing direction? We call this rectification. So rectification says, how do I make an alternating current stop alternating? Okay, so you have half bridge and full bridge rectifiers. So basically, let's say I have an input voltage, V in, and then I have what? V out, right? And then I have ground like this. So if I just connect them like that, then this is going to be AC if this is AC here, right? If I put one, what was it? It's just like just put a diode here. That's it, right? Yeah.
Is opposite. Yes.
Yeah. So I put a diode here. So we were playing with light emitting diodes just now, which is a subset of diodes. And a diode is basically a component, which, like I said, is magic inside. It only allows current to flow in one direction. So like how the LED has a long leg and a short leg, don't plug it in the other way, right? So the symbol for a diode is like this. It's a triangle and a wall. Okay, so the side that has the wall cannot accept current going into it. Current can only go the other way. All right. So when current goes this way, it will not flow into this branch. But when current tries to reverse, then it will be grounded. So therefore, we lose the bottom half of the wave, and we only have intermittent peaks of voltage like this. So this is a half rectified voltage, AC voltage.
There's a flat line over there. There's a small voltage.
What voltage drop?
Possible diode. Ideal diode. Okay, no,
Yeah. Everything we're talking about, by the way, is ideal components. Okay, so we'll dive deeper into like how components don't exactly behave the way you expect in next lesson, including diodes, if I remember correctly. But anyway, so we'll lose half the wave. So we're losing half the energy just from to the diode. So this is half wave rectification. It's very easy. It's just one diode, but it's not efficient because we're losing half our energy, right? So the alternative is a full bridge rectifier, which is like bloody annoying to draw. How much is it?
Four diodes. Yeah.
It's the diamond, yeah.
The diode. Yeah.
Okay. Joseph will draw the full bridge rectifier because I don't remember. Yeah.
I see. So it's actually just like when current flows on one side, follow that.
Yeah.
If it's like flip on the other side, you follow the other.
Basically, like we don't want to.
So.
What the fuck? It's like that's not your drawing, man. Yeah.
Like one bridge in the middle.
Yeah, there's one bridge.
Oh.
Oh man.
This is like
Okay.
Power supply in the center, right?
This is the output, right?
Wait, did you have to draw it to my
Wait. Oh, sorry. Let me think. So input goes into
Yes. Input is the cost list.
input, right?
Yeah.
Then wait, what the fuck? Okay. So this is what D in, right?
Yeah.
But why did I draw it? Wait.
Right. No, you have to
That's
flip this fuck. Fine. Just so you have to flip this diode.
This should be the output. This should be the output, right?
just look up the limits. So we die.
Should not last up the
Yeah. So this is the output. Sorry, this is the output. This this is the input, yes.
then
Yeah, so this would produce this waveform.
Yeah.
This VR will produce. The way that this is just
Yeah, so the bridge rectifier flips all the negative ones. It doesn't just delete them. So this will make like a better AC. Okay. Next lesson we'll talk about how we can make this a flat line after the full bridge rectifier. For now, I just want to introduce that to you.
full up, right?
No full ups. Okay, so yeah. Okay, so
Oh yeah, by the way, this is considered DC now.
yeah.
For some reason,
Because
because it's not
the direction is no longer changing. Yeah, so even though it's not flat, it's still DC because it's not changing direction. Okay, so this is the difference between AC and DC. So if you were to design components that circuits that plug directly to the wall, which you shouldn't be, then you would have to do stuff like this. Okay. But this is more of an FYI. Most people don't design AC circuits. And like if you are, then like you are starting to touch like power supply design. And power supply is magic box, and you do not want to be designing magic box. Okay. Okay. Any questions about AC and DC? Great. There's way more we could have talked about, but it's just not going to affect your life at all. So we're not going to touch it. Okay. All right. The last thing I wanted to talk about, which we have slides for, is power. I need to share screen again. This is terrible. Yeah. Okay. Power. Power is the rate of energy transfer. Okay. So remember how earlier we said that voltage is energy per charge and amperage is charge per second. So if I multiply the two, I get energy per second, right? So that's what power is. It is the unit of energy is joules. So therefore, the unit of power is joules per second. Okay. We can also use Ohm's law to eliminate either V or I. So I wrote it in blue over there. And we'll talk about this more later in the course. Okay. But for now, we just want to impress upon you that some small numbers like 5 volt, 1 amp is actually quite a lot of energy. Like if you think about it in mechanical terms, right? 1 joule is the energy required to accelerate 1 kg at 1 meter per second squared. That's kind of a lot of energy, you know? So your 5 volt 1 amp circuit is doing quite a lot of work for you actually. So that's why like motors are so nice because they'll consume like what 20 volt 3 amp and then it's doing like the work of like a human being. It's great. Okay. So this is going to also matter more when we talk about power loss in circuits as they heat up and as they just voltage drop across them. Okay, so I'll draw. You want to talk about this? Might as well, right? 5 minutes. I'll show power loss to resistance of wire. Yes. Okay, great. I have to fucking stop sharing screen again and then go to the. I don't know why, but KiCad does not show up at the window here. Oh, it does. It does. Just took a while. Okay, so here I have. Get rid of this stupid. Okay, I have this ridiculous circuit. I'll just make this 20R, whatever. Okay, so I've got some voltage across this, right? So my total resistance of this circuit is 30 ohms, which means that I've got what 0.33 amps through this whole thing. Correct? Yes, V equals IR. Yes. So 0.33 amps through each resistor. So let's say that this is my actual load. And this is some extra resistor that I have in my circuit. Okay, so this is touching on the idea of non-ideal wires. So right now we have these magic wires that have no resistance at all. In reality, they have resistance. So okay, this is 10 ohms is gigantic, but let's say it was 10 ohms. Then I'm losing some power to this. I'm not delivering all of my power to my load, which is this, right? So then I can very easily calculate this. So what did I say? P equals to IV, right? Which is I squared over R. So I can get my I squared, which is 1/3 squared, and then over R. So this will be P equals to I square R, which is equal to 1/9 times 10, right? So I've got 10/9. So this is huge. I'm losing an entire joule of energy just because this resistor is here. So when we are designing circuits that care about power, like stuff that's battery operated and you don't want to waste battery, suddenly you have to think about how much power each resistance in your circuit draws. Yeah, so we'll show you in future lessons when you really need resistors and how to choose resistor values such that they get the job done without using too much power. Okay, but for now, just for your information, you lose power every time you go across a resistor. Like the resistor will dissipate that power as heat because that's how resistance works, right? We take some of the current and we turn it to heat. Yeah. Okay. Yeah. Okay. Does anyone have any questions? Okay, great. For those who are going to be following along for the rest of the course, I want you to install KiCad. Okay. Okay. So our Rocketry Team Spacebar is sponsored by JLC PCB. So for the rest of this course, we are going to be teaching you not just basic circuits, but how to actually design your own printed circuit boards. And the eventual goal is that you have the confidence to design your own ESP32 development board. Okay, which I promise is fucking easy. Okay, so for those who are going to follow along for the rest of the course, you can install KiCad, which is the software that I've been using now. If you have time now, we can walk you through the installation now. If not, you can do it at home. Okay, and then like we'll be using KiCad for the rest of the course pretty much as you continue to follow along. Okay, KiCad. KiCad. English is hard. Yeah.